introduce Dr. Hal Weaver to give our presentation. Dr. Hal Weaver has been pursuing spaceborne, rocketborne, airborne, and groundborne investigations since 1978. He earned his doctorate PhD degree in physics from Johns Hopkins in 1982, and he performed first systematic investigation on UV emissions from NASA and NASA International Ultraviolet Observer satellite, providing the evidence that water was the dominant volatile constituent in the commentary. In 1985 and 1986, he made the IR observer of the comet Halley from the NASA Kuiper airborne observatory, which resulted in the first detection of water in comets. And for this reason, he was awarded the NASA Medal for exceptional scientific achievement in 1988. And in 1986, asteroid 1984 FN was renamed to asteroid Hal Weaver in recognition of Dr. Hal Weaver's work on the chemical composition of comets. And Dr. Weaver has led many investigations of comets using the far spectroscopic explorers and the NASA Hubble Space Telescope. And in March 2007, Dr. Weaver was appointed the co-investigator of ALICE ultraviolet spectrograph, which is one of the principal NASA's contribution to the ESA late Rosetta comet mission. And Dr. Weaver joined Johns Hopkins as a senior professional staff in the APL lab, and since 2002, and has been a member of the principal professional staff since 2006. He is currently the project scientist of the New Horizons mission, which is the first spacecraft mission to Pluto and the Kuiper belt. And in 2005, Dr. Weaver co-led a team that discovered 2 new satellites around Pluto, and he was also on the team that discovered 2 other small pollution satellites, P4 in 2011 and P5 in 2012. And let's welcome Dr. Weaver to give our the presentation.
Thank you very much, and thanks for coming, everybody. This is my first trip to Rochester, and it's a nice opportunity to see all the neat things you're doing here at RIT, and I appreciate that. But here today I'm going to be talking about the results from the New Horizons mission to Pluto and the Kuiper belt. This on the cover here is a little picture of our little spacecraft. It's about the size of a baby grand piano. Artist representation here. And it was just on July the 14th, 2015, so a little under 3 years ago, that the spacecraft passed just 7,700 miles above the surface of Pluto, doing the first in situ observation of the Pluto system. And this background image is an actual image from that flyby. This just blew us away. This is not noise in the background here. This is just after we flew past Pluto and looking back towards the sun. You see the horizon of Pluto and all these haze layers. And so most of my talk today, I'll be talking about these results from the New Horizons study, investigation of Pluto and its satellites. But before I get into the results, let me give you a little bit of background, and which provides some motivation for the mission. This is a cartoon of the solar system. You see the sun at the very center here. The first ring that you can really see is Jupiter, so the Earth and all the terrestrial planets are can't even be seen in the interior here. And the spacecraft took off from the Earth in January of 2000, January the 19th, and January 2006, and finally made it past didn't make it out to Pluto. It takes 9.5 years because Pluto is way out there, more than 30 AU from the sun. And the orbit of Pluto is this yellow curve, and just it's highly inclined. It's inclined by 17 degrees to the plane of the solar system, the ecliptic plane, and it's highly elliptical as well, which distinguishes it from the other planetary bodies inside of Neptune's orbit. The principal investigator for this mission is Alan Stern from the Southwest Research Institute. This is this is the very first NASA New Frontiers mission. This is a special line of intermediate-sized missions that NASA has, and this was the very first example of it. One thing I want to point out to everybody that you may not appreciate is the revolution in our understanding of the formation and evolution of the solar system that's taken place in the past decade. It's really been dramatic. The current architecture of the solar system, with the giant planets being where they are, it hasn't always been that way. We now think that in the early days, the first couple hundred million years of the solar system's existence, that the giant planets moved extensively in radial distance away from the sun. Jupiter may have come in as far as Mars' orbit and then gone back out again. We think that Uranus and Neptune actually flipped spots. So there was this incredible motion of the giant planets through the inner solar system that stirred everything up, okay, and finally settled out into what we have today. But one of the reasons why we think this is the story of how the solar system formed is because of the discovery of this, what we call the third zone of the solar system, the Kuiper belt, outside of Neptune's orbit. This cloud of particles. In fact, I forgot to mention, in this cartoon, all the white dots are representing bodies in the Kuiper belt, which is a roughly donut-shaped region around the sun. Okay, and Pluto stood out like a sore thumb for many, many years, but finally people realized it was just in a typical orbit for a Kuiper belt object. Okay, this is the view looking down on the plane of the solar system. You project everything of every known object in the solar system. Over here to the right, the yellow dots are the Kuiper belt objects, and we're up to about 2,000 have been discovered. The first one was in 1992, except if you go back to Pluto, which was discovered in 1930. Okay, we now realize. Okay, roughly 2,000 have been discovered since 2002, and the numbers keep going up every year. We think that there are probably more than 100,000 objects larger than a couple hundred kilometers out in this region. It's the most populated region in the solar system. Inside of the Kuiper belt, even more populated than the asteroid belt between Jupiter and Mars. Here are the so-called Trojans, the Lagrange special places in space where the gravity of Jupiter is exactly balanced by the gravity of the sun. And a bunch of the bodies that were moved around during that radial migration of the giant planets ended up here. In fact, that's the next mission I'm going to be working on. Is a mission that's called Lucy, to fly by 6 objects in the Jupiter Trojan region. Okay, we think that it's called Lucy because it's not an acronym. It's looking back to the formation of the solar system. We think that the bodies, there's a very diverse set of bodies in these regions, and we think that those were collected from different radial distances from the sun, and that's the reason for that diversity. The explanation of this and the different families of objects that are in the Kuiper belt is what has led us to really believe that there was this tremendous radial migration of the giant planets during the first couple hundred million years of the solar system's existence, because we can explain everything if we postulate that. So it's started in the early 2000s. These ideas were seriously being considered, and the correspondence between the predictions of these dynamical models and what we actually observe in the solar system has just been getting better and better, which is what you expect from something that's really truth. Because otherwise, why would you believe that this is the story of the solar system's formation? Okay, so Pluto, instead of being this outlier, because of this highly elliptical orbit and also its inclination out of the plane of the solar system, is now become another member, even though it is the largest member of the largest known member currently of the Kuiper belt. It's the gatekeeper to the Kuiper belt, essentially. The little caret symbols here are all the known comets, which can come in from any direction. The periodic comets we think came originally from the Kuiper belt, but the ones that are coming in at nearly 90 degrees to the ecliptic are coming from the Oort cloud. That's the biggest object in the solar system that extends from about 1,000 AU from the sun out to 100,000 AU, halfway to the nearest star. Okay? And there are probably close to 1 trillion very small bodies out there. Looking at it from the side, you can start to see that torus-shaped arrangement for the Kuiper belt objects. This is Pluto's orbit, is this purple thing here. Okay? See, it goes both above and below the plane, but like I say, that's typical. Comet Hale-Bopp, which is a long period comet, came in at almost 90 degrees. This is a famous comet that appeared in 1995. Okay? Just showing you a different kind of way of looking at this. This is a plot of the semi-major axis of all the known bodies out there in the Kuiper belt as a function of semi-major axis and inclination angle. Okay? So this is, Pluto's is sitting here, yellow, at 17 degrees. Neptune is here. This is the semi-major axis of Neptune. So there are these different families, 3 different families of Kuiper belt objects. They're the so-called resonant objects, which the 800-pound gorilla out there is Neptune, which is it's one of the giant planets in the solar system. And its orbit, its gravity perturbs some of the Kuiper belt objects. It creates, but it captures some of them are captured into resonance with Neptune's orbit, like Pluto and all of the objects that are lined up here with the semi-major axis at about 40 AU. Those are called the Plutinos. They're in a 3-to-2 resonance, orbital resonance with Neptune. So every time Neptune goes around 3 times around the sun, they go around the sun. Okay, and that's a stable configuration over the age of the solar system. So that's the Pluto system is there in yellow. The ones in the magenta objects here are so-called scattered Kuiper belt objects. These are ones that their orbits have been really agitated by Neptune's gravity, and they are highly elliptical and highly inclined orbits. Some of them get injected into the inner solar system and become the short period comets. And that's what I'm trying to depict here. For example, comet 67P Churyumov-Gerasimenko, which was the target of the Rosetta, ESA-led Rosetta mission, originally we think was one of those objects and made its way into the inner solar system, okay, over a period of tens of thousands of years. And these yellow objects are what we call centaurs. They're on their way to becoming short period comets. Okay, they're not dynamically stable in these orbits, but they come all the way. The centaurs, by definition, mean that they have their perihelion, their distances from the sun between Jupiter and Neptune. Okay, so they come inside of Saturn's orbit. So the fact that we have these different families of objects, like I say, was that could only be explained by having this massive radial migration of the giant planets. Oh, and then one other thing I wanted to say was, so we've flown by Pluto already. We're now headed, and then we had the other mission that went to a scattered body. We have an opportunity with the New Horizons mission to fly by the third category, the third family of objects, and that's this object right here, which was just discovered in 2014. It's called MU69. We've just had a naming contest. It'll have a better name within the next couple of months. But this is what's called a cold classical Kuiper belt object. Okay, so it has an inclination of nearly 0 degrees, just a couple of degrees. It has a nearly circular orbit around the sun. And because of that, we think that it has been basically preserved since the time of the formation of the solar system 4.6 billion years ago. It looks now probably like it did then, and this may be the most primitive object ever observed by a spacecraft close up. So that's why we're excited that on New Year's Day of next year, the New Horizons spacecraft will fly about 3,000 kilometers away from that object. That's our next target. Okay, so the New Horizons mission. The single biggest object on the spacecraft is this radio dish, which is 2.1 meters across, so 6.5 feet across. So it's like, we like to say it's about the size of a baby grand piano. And this is an artist representation. These are all of the instruments that we're flying. We have a sophisticated suite of instruments that could do a lot of different things. We have color cameras, an infrared spectral imager. This is used for composition, measuring the composition of the surface, an ultraviolet spectral imager for atmospheric studies, the long-range reconnaissance imager. Here, all the remote sensing instruments are all aligned, are aligned in what's called the -X direction of the spacecraft. That's our highest resolution imager. We have a radio experiment, which is the electronics associated with this radio receiver that does a really neat experiment. As the spacecraft flew past Pluto and into Pluto's shadow, that antenna was pointed towards the Earth, and we were radiating radio waves up to the spacecraft, collected by that antenna. By watching the bending, the change in phase of the radio signal as it passes through Pluto's atmosphere, you can deduce the average molecular weight and the temperature profile of the atmosphere. So that was one experiment. At the same time, because when you're out at Pluto looking back at the inner solar system, the sun and Pluto and the sun and the Earth are nearly, they're only a couple of degrees apart from each other, 2.5 degrees apart. So at the same time we were doing that uplink experiment, that was 80 kilowatts of radio power being sent up. We were also looking at the sun with the ultraviolet instrument, looking at absorption of molecules in Pluto's upper atmosphere to take inventory on what's in Pluto's upper atmosphere. And I'll say a little bit more about that later. We also had a couple of experiments that measured both low energy plasma coming from the sun and the solar wind. That was called the SWAP, solar wind at Pluto experiment. And then higher energy particles, which pick up interstellar ions coming in and also escaping ions from Pluto's atmosphere. Pluto does have an atmosphere. It's actually almost the same composition as the Earth, mostly molecular nitrogen, but about 100,000 times less dense than what we have in this room. But there was also a student experiment that's underneath the spacecraft. It's called the Venetia Burney Student Dust Counter. This is a series of 14 polyvinyl chloride panels that, when the spacecraft was flying through space for most of the time, just between the Earth and Pluto, flying with those panels facing the RAM direction and measuring dust particles that hit those panels. And once we got outside of Saturn's orbit, these were unique measurements that hadn't been ever done. And this was proposed, designed, and built by students, both undergraduates and graduates at the University of Colorado in Boulder. And they just did a fantastic job. I mean, I thought that was a party school, but they were the first, the first instrument to be delivered. And it's done some nice science as well. The power for the spacecraft was provided by a radioisotope thermoelectric generator, and that's this thing that looks like a hair thrower coming out the back, black. And we used plutonium-238. We used spare leftover from the Cassini mission. The radioactive decay, it produces heat. It's actually physically hot and drives thermocouples, which drive electricity to the spacecraft. We started out at launch with about 240 watts. By the time we got to Pluto, we were down to about 200. But that was plenty to run the mission. And just to show you, since this is RIT, I figure you see, might as well see the hardware itself. These are the instruments that we flew that you saw on the previous page. The interesting thing about this mission is, because we were going all the way out to Pluto, it takes a lot of energy to get out there. We had to try and miniaturize as much as possible, and since we had limited power with the radioisotope, with the RTG, we wanted to make it highly energy efficient instruments. All together, all of the instruments weighed less than 30 kilograms, so about 60 pounds, and they drew, if they were all on at once, less than 30 watts. So for about what you need in your nightlight, in the bathroom, you could drive all of the instruments on New Horizons simultaneously. And there's the student dust counter, by the way, those panels. I had to bring this up because I'm at RIT, and we have somebody who's actually used LORRI data. LORRI is the high resolution camera, which is also a It's a 20.8 centimeter telescope, so 8-inch telescope, which is pretty big for a space mission. It's extremely sensitive, and Michael Zemkov and she here have wanted to use this to measure the cosmic background radiation at visible wavelengths. And they took a stab at some of the early data that we took to see whether or not it would be useful for that, and here's the data over here. Of course, everybody knows that the COBE experiment and the WMAP experiment, Wilkinson microwave anisotropy probe, that's what the Nobel Prize is awarded for mapping the cosmic background radiation at microwave wavelengths. Well, you'd like to extend that into the near infrared, into the visible, and even into the ultraviolet to try and figure out what was going on in the early universe. And this is another way, so the LORRI instrument is providing some input to that. And this is a paper, recently published in Nature Communications. And this just shows, and the advantage of New Horizons is because when you're at Earth or any Earth-based observatory, you're trying to look through the zodiacal cloud, which is this dust debris in the inner solar system generated by what's in the asteroid belt that is reflecting sunlight and basically blinding you for doing sensitive measurements of the background radiation. New Horizons is way past that, out beyond Pluto's distance, so it can avoid that particular problem. Okay, so I always have to show this just because if you're in the rocket business.
2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft.
2 p.m. on January the 19th of 2006. This was our third attempt. We had bad weather the first couple of times that we could possibly.
And continues to look good. As the Atlas V vehicle
this is an Atlas 551, the most powerful rocket available in the United States.
The New Horizons spacecraft on its way.
Had a main engine plus 5 solid rocket boosters around it, providing several million pounds of thrust for about a 1,000-pound spacecraft. So we were, and it was a couple 100 feet tall, and we had our 6.5-foot tall spacecraft sitting on the top of that. It's like the hood ornament on a car. But we needed that in order to get to Pluto in a reasonable amount of time. It was, fortunately everything just worked beautifully. It was the fastest spacecraft that still holds this record ever to leave Earth. Traveling at 36,000 miles per hour. This thing took off. It didn't look like it was that fast when it first took off, but it was over the Indian Ocean in 45 minutes, and then the Centaur upper stage, kicked in, and then we had a third stage that then kicked us out to the orbit towards Pluto, and it passed the orbit of the moon in only 9 hours. Okay, and we had a full moon that night, and I remember going to the hotel after the lunch and looking out at the balcony and saying, my gosh, you see the beautiful full moon. This is at 11 p.m. and thinking that the spacecraft has already passed the orbit of the moon. It took the Apollo astronauts 3 years to get there, 3 days. That would be a tough one. Maybe to Mars, but not to the moon. Anyway, what we were trying to do, we had to hit that particular launch window in order to be able to fly close to Jupiter, fly through this little keyhole in space behind Jupiter that allowed us to steal some momentum from Jupiter, accelerate the spacecraft by more than 20%, and cut 3 more years off the travel time to Pluto. And that's why we were so anxious to launch when we did, and we did, and we were successful. And we flew by Jupiter, and we hit that, we got the speed boost, but in addition, we got a lot of nice science at Jupiter as well. We actually passed closer and closer to Jupiter than the Cassini spacecraft did on its way to Saturn. But one of the things we did was, you see this? You see the animation here. We actually observed, this is the best example of a extraterrestrial volcano ever taken. This is by the LORRI instrument on New Horizons. This is the Devastar volcano on Io, the closest Galilean satellite to Jupiter. And Io is just being heated like crazy because you get giant Jupiter sitting there, 320 times as massive as the Earth. And the tidal friction created internally in Io is just churning it up and creating, this is the most volcanic object in the solar system. And this thing was just popping off the whole time we were flying by, and we got a chance to look at it. We actually measured velocities of the dust. This goes up 3,000 kilometers above the surface. This material is going up and then coming back down. This just shows you, graphically and in color, the path of the New Horizons spacecraft, year by year. It shows you how we crossed each of the orbits of the giant planets, but of course those planets were way far away from us at the time we flew by, and we finally got to Pluto in 2015, July of 2015. This is just another view of that trajectory. The spacecraft is coming in from the lower right here. It's like we're going through a bullseye. These tick marks are every 10 minutes. So we were humming at over 30,000 miles per hour, past Pluto, and we were trying to make those observations. But one of the mission design criteria was to fly through the shadow of Pluto. The sun is over here to the right, and the Earth is over here to the right. We flew through the shadow of Pluto and the shadow of Charon in order to make these special measurements. But this happened, on July the 14th was the time of closest approach. Just a very high level, we had a whole laundry list of objectives for this mission, but just, basically, for the very first time, we're going somewhere close to this object, and we can do get detailed information on what the thing really looks like, what the composition of the surface is, and characterize its atmosphere. This is the best Earth-based observation of the Pluto system, the deepest image ever taken, which is by the Hubble Space Telescope, Wide Field Camera 3, with Pluto and Charon, the binary planet pair there. Dynamic range here is about a factor of 100,000, over 100,000, because in order to be able to see Pluto and Styx here, these are just pinpoints of light, but all of the satellites of Pluto, all of the objects except Charon, were discovered by Hubble Space Telescope. And it was really cool because once we worked out the dynamics of the system, this is what you get. This is a little cartoon showing you as you walk out from Pluto here to Charon, Styx, Nix, Kerberos, and Hydra. They're all in the same plane, the equatorial plane of Pluto, okay, going around in almost perfect circles. And that kind of screams out at you that they were all created in the same event. And what we think happened was there were two roughly Pluto-sized objects that had a glancing collision, and they were partially differentiated objects that then tore off the mantles into a debris disk that formed around now you had two large objects going into orbit around each other, and then in the disk that was formed, the planetesimal disk, this is like a little mini solar system. You had the formation of these small satellites. Okay. So this is the best view ever taken from Hubble. Believe it or not, some of my colleagues spent, a decade looking carefully scrutinizing images like this. And the neat thing is, if you watch, Pluto has a 6.4 day rotational period. Pluto and Charon are tidally locked with each other. They go around every 6.4 days. You can actually see that brightness is changing in those images. And from these kinds of observations, we could tell that Pluto actually had pretty dramatic brightness variations, and it had color variations as well. It's one of the most, turns out to be one of the most variegated objects in the solar system, just from these kinds of data. But this is what you get from a spacecraft flying by. Okay, this is the same scale. Okay, so you can see, there's this bright spot here corresponds to this, but who would have thought that this is this huge sheet of molecular nitrogen ice? This is what we know from the spacecraft results now. And it's incredibly bright. It reflects about 80% of the sunlight incident on it, and it's really the source of all of Pluto's activity. Really, that giant sheet of molecular nitrogen ice, as I talk about in a little while. But also, can you make out this is, one of the media people from NASA was calling this the heart of Pluto. Kind of shaped like a heart, and the left ventricle is this region that we now call Sputnik Planitia, and this is the official name now for this region. But there was this dark red band here, and this color variation over the surface. This is our best estimate of what it would look like to the human eye. We didn't have filters that were optimized to that were exactly what the human eye would detect, but by putting together the colors in the right combinations, this is our best estimate. But we have color filters, and by putting those data together, we now have a lot more information about the compositional units across the surface of Pluto by doing that. So this is our best color view. It's false color, but it's telling you that there's significant variation in composition across the surface of Pluto. And this is our new family portrait. Instead of having those little pinpoints of light, you know, we have real worlds with real complexity is shown here. Here's Pluto, and these are drawn to scale. Okay, this is Pluto. Charon's about half the diameter of Pluto, and you have, you know, Styx, Nix, Kerberos, and Hydra, and then we blow them up a little bit here because we did resolve the small satellites, and since we discovered them just before Nix and Hydra, just before the launch. We could actually put some observations of them into the observing schedule. Kerberos and Styx were discovered so late that we couldn't really, you know, plan too many observations. Then the whole purpose of the mission was really get Pluto and Charon, but we still squeezed out some resolved observations of those. But this is a very dramatic difference, and this shows the advantage of doing spacecraft exploration of the solar system. And this is almost at the 50th anniversary of the Mariner 4 flyby was to the day. Mariner 4 flyby of Mars. You know, if you want to really find out what's going on, you know, at these bodies in our solar system, you have to go there. And you know, it's just been remarkable over the past 50 years. You know, we've gone to, you know, all of the bodies. This sort of closed out the classical planetary region, the observations that New Horizons made of the Pluto system. And here I just wanted to point out that Pluto is weird in a lot of ways. I mean, it has the highly inclined orbit, the highly eccentric orbit. The pole is also flipped over relative, instead of being perpendicular to the ecliptic plane, is flipped over 100 degrees. And so you get these really strange seasonal effects. You know, the seasons are, you know, the tilting of the pole, you know, is what causes seasons. And the same thing on the Earth. But you know, so Pluto, this is you know, just shows you starting in 1887 or 1866 at aphelion, out at 48 AU. As you go around, the orientation of the pole of Pluto as you come around, and here's where we let's see, yeah, where we finally observed it over here. Okay, in this configuration. And we've had people on our team look back millions of years, integrate the orbit back, and you know, it turns out there's 3 million year cycles because the pole is not fixed in space; it actually nutates around a little bit, and that causes what we call Milankovitch cycles in Pluto's climate. Okay, so it has really weird. So you kind of have to get your head around this. Think about it in 3 dimensions to really understand you know, what's going on Pluto. And this just shows you, we have this zone around the equator of Pluto that always sees sunlight diurnally. So as Pluto's rotating, like I say, 6.4 day period. And those regions, those latitudes, and the, you know, between plus and minus 13 degrees around the equator, they see the sun you know, all the time, you know, every Pluto day. But there are some places that, you know, only see the sun in very limited portions of Pluto's orbit, and that's what we think. These are projections of the images of Pluto onto these cylindrical maps, and this is what it looks like, and we think that produces the morphology that we see. And the other thing I want to get back to, so I said that giant region, Sputnik Planitia, which is you know, like 1,000 by 1,400 kilometers in extent, 900,000 square kilometer region. This is a giant sheet of molecular nitrogen ice, and Pluto is extremely cold because it was at 32 AU from the sun at the time we flew by. The surface temperature is about 38 Kelvin above absolute zero, so minus 390 degrees Fahrenheit, you know, minus 240 degrees Celsius. Okay, so water is like a rock on Pluto. You know, it's so far below the freezing temperature of water, 273 degrees Kelvin, that it's more like a rock than an ice. But molecular nitrogen ice, you see where the triple point of it is right here. These are the 3 main volatiles, ices on Pluto's surface: molecular nitrogen, carbon monoxide, and methane. Okay, those 3 things are still active, even though Pluto's surface temperature ranges from 30 Kelvin to 50 Kelvin, depending on, you know, where you are. Molecular nitrogen still has enough vapor pressure that it can sustain an atmosphere and also move around on the planet. You have motions of that gas, you know, the sublimation and condensation taking place. Okay, so now what I want to do is focus on the heart of Pluto, the Sputnik-Planitia region, and show you a movie in just a second. First of all, we think there's been some controversy internally on the team about what Sputnik-Planitia really is, but the majority of people think that there was a giant impact that occurred shortly after the Pluto-Charon system formed, creating a huge basin, and then got filled in with the molecular nitrogen ice. Preferentially, if you do the modeling, the molecular nitrogen would preferentially condense into this basin. We think that that basin is at least a few kilometers thick, and maybe as many as 10 kilometers thick. We've done some modeling of that. But this is a digital elevation map, and then you can see the scale over here, -3 kilometers to +3 kilometers. It's, you know, this basin, but then it's kind of flat across Sputnik-Planitia. Okay, so this is an incredible picture. These are real New Horizons images put together in a movie as if you were flying across. This is coming from the bottom end, the south end of Sputnik-Planitia, over the, you know, there's a mountainous terrain over there, and then flying around the edge of Sputnik-Planitia. And this has been a digital elevation map. This is exaggerated a little bit in the vertical dimension, but these are real images, you know, taken by the New Horizons. And you look at that along this incredible, you know, this is the western side of Sputnik-Planitia. Look at the geometrical patterns in the in the giant nitrogen sheet, and all of these other features. You see all these craters in some regions. We did not find a single crater on Sputnik-Planitia, which suggests that that is a very young region. You know, probably no more than no older than 10 million years old, and maybe even, you know, active now. We think it is. Okay, so that was a beautiful movie put together. Now let's just run around the periphery and just show you highlight some specific things. So there's this rheological cycle on Pluto involving molecular nitrogen ice. It's sort of like the hydrological cycle that we have on the Earth with water ice. This molecular nitrogen ice, it's like a glacier, like a water glacier on Earth. It moves, and you can see. And by the way, this is you have a little figure over here showing you the part that's being expanded, magnified in this picture. Okay, so you look over here, you see where that is. But look at all the you see the barriers here, the little swirly things. This is that molecular nitrogen ice, which is active at these very, very cold temperatures, moving past the barrier. You know, we have we think that this is evidence that there's like a glacier moving. And this, let's see if I can get this to run. This is that, you know, in the middle, showing you these geometrical patterns, and we think this is like a lava lamp. We get the radioactive decay in the interior of Pluto, which is not very strong, but it's enough, and this molecular nitrogen ice is volatile enough to heat it up from below, and it acts like a lava lamp. You get the stuff heated up from below and rising to the surface and cooling and then falling back down again. Okay, so that's what we think these geometrical patterns are caused by, and this is, you know, actual modeling of that. You know, you can see, you know, Teresa Wong at Washington University in St. Louis, you know, put together this simulation. This is a paper by Bill McKinnon that appeared in Nature. So we think we have some explanation for what's going on there. We have these other interesting regions. Here you can see where there's pits. We think those are sublimation pits where the sun has come in and, you know, preferentially sublimated a lot of material. And then there's these highlands over here, this really rugged mountainous area. The ices, the molecular nitrogen ice, is sublimating in this region and moving to the east and recondensing and then flowing back down. You can see flow patterns as you come back down. These are these giant, we think, primarily water ice mountains. Okay, they're as high as the Rocky Mountains in the United States. These mountain ranges here. You can see the scale here. This is 50 miles across. But these are mountainous regions. And the only thing that's strong enough, molecular nitrogen ice by itself is not, but water ice is, we think, the bedrock that's underneath a thin coating of the volatile ices. We think that we've actually seen evidence for what we call cryovolcanism. So it's, instead of regular volcanism where you have a hot material, the magma coming up from below and being shot up into the atmosphere, you have material oozing out that's very, very cold, but is warmer than the surroundings, and it's coming out of this hole. You see right here? This is several kilometers deep, and you get a ton of stuff coming out here, and there's a mound around it. I don't have the vertical scale here, but it's a couple kilometers high. And we think that's evidence. And there's another example of it somewhere else as well. This is the region that we call chaos on Pluto, giant blocks. And once again, you look at the scale here. We see something similar on one of Jupiter's icy moons, Europa, which is NASA's building a mission to go to Europa now, but much larger scale actually on Pluto. The scale bar up there, 50 miles. These are giant blocks of water ice that have been turned over by the action of the molecular nitrogen ice, and this is the edge of Sputnik Planitia with this molecular nitrogen ice. Notice a pool of that molecular nitrogen ice left here. Okay, this is a pretty big pool, nearly 50 miles across, and then this, we actually see stratification in the, it's like going to a canyon and looking across and you can tell something about the epochs of geological formations by analyzing data like these. And then we had this really weird region that we haven't, it has an analogy to the Earth, which I'll show you in a couple of minutes, but we originally called this the snake skin region, these aligned features here. They're all lined up and they're like a couple of kilometers across, separation, just regular pattern, and they're rich in methane ice on their peaks. But this is the analogy on Earth. We think it's driven just by the solar insolation, the way the sun is coming in and eating away the molecular nitrogen in between these cracks, and it, by modeling this, similar to the way we model penitentes on the Earth. This is in high, some mountainous regions. This is in Chile. You see these things. They call penitentes because they look like angels, sticking up with their, But these are, look at the scale here. These are like people-size scale, and on Pluto we're talking about, much bigger features. There's the Pluto stuff up there. But we think the similar mechanism for explaining it. And then we have this dark belt going around the equator of Pluto. What the heck is that? That's, we think, heavy organics, okay? That the haze that you saw in that very first cover image that I have rain down on the surface and get hit by cosmic rays or ultraviolet light or solar wind, or just on their way down, they get broken up and reform into heavier hydrocarbons, and we think that's what we're seeing here. And these are heavily cratered, indicating this old stuff. This is organic material. We actually have climate modeling done, three-dimensional climate modeling done by some colleagues in France who do similar modeling of the Earth's atmosphere and also Mars. They've applied that model to Pluto, and they show, start with this initial distribution, but knowing the weird orientation of Pluto, and if you did have this basin created by an impact, you'd naturally end up with this here, which looks like a pretty good match to what we actually observed. And this is a compositional map compared to their model here. So we have this infrared spectral imager that can map out the different species, the volatiles, the ices, the molecular nitrogen, the methane, and the CO. And these are the maps, and it matches, once again, the model. So we think we have a decent understanding of what's going on there. Okay, so this, at the time of the flyby, on July the 14th, we had a very limited downlink capability. We just had some compressed images, so these are JPEG compressed, and they had artifacts in them, just a very limited amount of data that we could send down. We had to wait until early September to start systematically sending all the data down. And this is the first thing that one of the first things that came across my desk. This is Labor Day weekend in 2015. When I saw this, I almost fell out of my chair. just because this is that view looking back towards the sun. And just look at these are you see the shadows of the mountains here. This is Sputnik Planitia, and there's very different phase angles. So it doesn't look like that white sheet. You know, you see the scattering off the surface, and you see all these mountains. But this is not noise on the horizon. These are bands of haze, and we count up to 20 layers of haze going up to several hundred kilometers above the surface. It's maybe similar to the haze we see on Saturn's largest moon, Titan, over here to the left. Similar haze was seen by Voyager passing by Triton, the largest moon of Neptune. But then you have this, I think it's, let's see if so flying past Pluto and then looking back, you see this thing lit up all the way around. Okay, so that just tells you, because you only see a little sliver. If you're looking at scattering off the surface, you see the whole thing around because that's atmosphere, that's haze in the atmosphere that you're seeing. And it preferentially scatters blue light, just like we have here. Blue sky, this is the blue sky of Pluto. This is not a fake, this is real. It's preferentially, strongly scatters blue light. This is just an example, and where we see the Pluto's atmosphere compared to Titan's. Okay, there are a lot of similarities, and, in Triton as well. This just shows you in a little bit more accurately the geometry of that neat experiment that I was telling you about. The plane of the ecliptic, the spacecraft coming in here from the right-hand side. This is the line followed. We were trying to hit the center of the shadow of Pluto. So you get the sun over here shining across Pluto and creating a shadow. We wanted to hit the center of Pluto, and then given that, we tried to also go through the shadow of Charon, but we couldn't make it to exactly the center, but we get a piece of Charon. And when we went by Charon, this is the signal that we saw from the ultraviolet spectrograph, okay? We actually did this at all the different colors in ultraviolet wavelengths, but this is just the total signal. As the spacecraft flew into Charon's shadow, looking at the absorption of sunlight as we went by there, and it just dropped like a rock, straight down, indicating a sharp edge, no atmosphere. If you compare that to Pluto, you see how different it looks? How it's bent like this. This is because Pluto has an atmosphere. It's about 10 microbars, so 10 to the minus, Earth is 1 bar, okay, so you got 10 to the minus 5, less atmosphere, but we see it very clearly, and we were able to map the composition of that atmosphere and the temperature and mean molecular weight all the way down to the surface by combining the ultraviolet and the radio signal. And this is just that nice view. This is a lot of people's favorite, just looking back at Pluto and just seeing the blue sky. And this is that whole family again. Let me just say a few words about Charon. Charon had two huge, the two things that really stand out about Charon are, first of all, this dark reddish polar hood that you didn't know about before New Horizons went by, and then this giant chasm that goes all the way around the equator of Charon. We're talking about 1,000 kilometers across and several 5 or 6 kilometers deep. It dwarfs the Grand Canyon in the United States. That huge chasm, which goes almost all the way around, we think was caused by the freezing of water ice that was, so after the two bodies collided with each other, to create Pluto and Charon, everything was hot. You had liquid water underneath the surface, and then that froze and basically broke Charon apart at the seams. Okay, just caused the extensional terrain that you see here. Now this thing is interesting because this is the first example of this that we've seen in the solar system. Pluto has an escaping atmosphere. We were surprised to see that the main escapee was not molecular nitrogen, which is by far the most abundant species near the surface. But it turns out the upper atmosphere turned out to be much colder than what we originally thought it should have been. It turns out that the species escaping most easily is methane. Methane is flying out, escaping from Pluto's atmosphere. And it gets focused, the methane molecules get focused by the gravity of Charon, and then it's cold enough in the polar regions of Charon to condense. And that's what we're seeing here. Mass transfer from Pluto to Charon. And then once that ice is pretty much clear, if you look at methane ice in the lab, it's just clear. But that methane ice gets hit by cosmic rays and ultraviolet light and solar wind over the age of the solar system, breaks the bonds in the methane, and they reform into more complex hydrocarbons, similar to what we saw on the surface of Pluto. And that's what we're seeing here. We didn't get a direct view of the southern hemisphere of Sharon, because in order for this hypothesis to be correct, you have to see it at both poles. But we actually we got some information on the south pole of Sharon by looking at Sharon in reflected Pluto light. Okay, and we saw that, and it was darker, and so we think that is a viable explanation. Let's see. So, and this is just a digital elevation map, just showing you how deep this the chasm is, and this is just explaining, which I won't go into, the mechanism for transferring the methane. Now these are our small satellites. These are our best images of those small bodies, and they come in pairs. Nix and Hydra are approximately the same size, roughly 40 kilometers across. That was big enough that we could actually count craters on the surface, and that's how you age date the surface. Because you have a model telling you how many small bodies are flying through the Kuiper belt, at these distances, and then you count up the number of craters and compare the numbers, and we now from that kind of analysis, we know that the ages of the surfaces are very old. It's like 4 billion years old. These objects they're like little ice balls, it looks like. And then that goes back to that formation scenario that I was telling you about before. We ripped off the ice-rich mantle of the Pluto, of the proto-Pluto and proto-Charon, that then created an icy disk, and within which you had these small bodies form. And you look at this looks like a bilobed object, sort of like Churyumov Gerasimenko. It's just telling us something about the formation mechanism for small bodies in the solar system. This is just a little movie showing you the other interesting thing about the small bodies is that they're rotating much faster than being tidally locked to Pluto. The outermost Hydra has a period around Pluto of about 36 days, but it's rotating a 10-hour period. Okay, that's like the moon. The moon is tidally locked, so we only see one phase, and that's how all the other satellites in the solar system are, but that's very different than what we see here. Not only that, but the poles are tipped over almost 90 degrees from what we originally were expecting. And this is just once again showing you the counting of the craters, and we can tell about the age. We also got these infrared spectral measurements, and this is why we know that the surfaces are dominated by water ice from these strong bands. Here at 1.5, this shows crystalline water ice, mostly crystalline water ice, in the 2-micron band for both Nix and Hydra. We got excellent data that told us this is the fingerprint of molecular nitrogen of water ice. But if you subtract off the model of the water ice, you're still left with a significant feature over here at about just above 2.2 microns. And our best guess for that is it's an ammoniated species. It's not ammonia hydrate, it might be ammonia chloride, actually. And we see that in another satellite system that was formed by a giant collision. This is the Haumea system. Haumea is another dwarf planet like Pluto is. It's rotating very rapidly, though, and we've identified a family of objects associated with Haumea, and one of its satellites also shows this little feature at 2.2 microns, and Haumea does itself. So, we think we understand why, and it's very different from most of the other small Kuiper belt objects, actually. This was a great hit with the public when we flew by in midsummer. We got the cover of the New York Times. We colloquially call the first set of high resolution data that we send down. We call these is our New York Times data set. And so sure enough, we got that, and lots of coverage, many newspapers, but we're not finished. Okay, we've now left Pluto's in the rearview mirror. We're actually flying right now through the densest portion of the Kuiper belt at 43 astronomical units away, And we identified in the summer of 2014, this was no easy task, but we found a body, we had enough fuel to move the spacecraft to a flyby of this object. Right now it's called 2014 MU69. It's going to get a new name shortly. But we're going to fly 3,000 kilometers above the surface of this thing. And this is in that separate family, this new family of Kuiper belt objects that have never been explored, and maybe the most primitive object in the solar system. We have occultation, stellar occultation observations that we did this past summer, the team did this summer, that indicates that it could be two bodies there or a bilobed object. That came from the occultation results. But it's New Year's Day of next year is when the flyby occurs, and then a couple of days later we'll have our best images come down. So please pay attention at that time and celebrate New Year with the MU69. Thank you.
We just have one question's time.
Yeah, sorry about that. I'm happy to answer questions outside if people want.
So, thank you very much for your talk. After all we've learned through New Horizons, what science question and/or instruments would you prioritize for a future Pluto mission?
Yeah. Well, our teammates are right now considering an orbiter, a Pluto orbiter. I mean, you'd like to not just fly by really fast, but you fly an orbiter, you'd add like a mass spectrometer, to actually, do in situ compositional measurements with, incredible, resolution and fidelity. So that would be the new thing, and then thermal infrared, mapping also to gain information about the thermal inertia of the surface and stuff like that. We had a radio observation now, which gave us some information, but very poor resolution. So I think those are, other than the things we already, have flown, those are good things to fly as well. Okay.
Yep. For any other question, please, we have reception. You can
ask questions there. Yeah, I'd be happy to talk to you. Thank you.
Okay.
Sorry.